In this tutorial, I'm gonna cover how to create. I'm gonna show you how to create. How to create. Hi, this is VJ Fader. In this tutorial, I'm gonna show you how to create audio spectrum analysis in Niagara particle system. Many of you have requested this tutorial, so here it is. We're gonna make something like this. Take a look. Cool, let's dive right in. So I have a Niagara system created here. It's almost blank. I already got started here to save some time, but I can walk you through on what I've added here. The first thing I changed is I changed from CPU simulation to GPU compute simulation, just because you want to utilize the GPU power so you can push a lot of mesh particles in Niagara. I normally go with GPU simulation, and when you do that, you have to take this fixed bounding box option. What that does is you can determine within a certain bounding box that this Niagara system will appear in front of the camera. So I normally just put a really huge value here, for example 10,000 in minus and then 10,000 in plus. And the other thing I've added is spawn burst instead of spawn rate. It instantaneously makes however many particle you designate. So in this case, I put spawn count as 10. I put the spawn time as something really small, 0.01 per second, so that it's constantly pumping out 10 particles. If we take a look at the preview, I'm going to drop this particle system onto my level here. I'm going to drop it in the center, reset the position. You can see, there's only one cube. Basically, all of the particles are all spawned at the same location, all on top of each other. So that's why you only see one cube here, even though there's hundreds of cubes. And quickly, I want to go over particle mesh renderer. I disabled the sprite renderer because I normally go with a mesh particle. So in the particle mesh, I picked something very simple. So I picked the default cube. By the way, I'm using the starter content assets. So here I picked a cube, and the cube, as you can see in the details, it only has 24 vertices and 12 triangles. So it's kind of one of the most basic mesh you can have available. That's kind of, you can use that as sort of a benchmark. So if you go higher in the mesh count, then you might have to have lesser number of particles depending on your GPU power and your computer. For the material, I take the override, and then you have to add an element so you can assign your custom material for your mesh. And in this case, again, I picked the stock MTech hex tile. So basically, I created a blank Niagara particle system, and this is the settings I have so far. And then we're gonna get into visualizing our particle system using spectrum particle system using audio spectrum data. Add a spawn location. Instead of everything spawning from a point, I'm gonna use a torus. Under particle spawn, I'm gonna hit plus and then type in location and then pick torus location. I'm gonna set the radius to say something like 200, handle radius to be 0. So torus is like a donut, handle radius is basically how thick your donut is, and I'm gonna set that to 0. So essentially I'm just creating a ring here. For the axis, I want this to point towards me in the x-axis, so I'm gonna take the torus axis checkbox and then put that x value to 1 and then z value to 0. We can hop back into the level and then see that, alright, we got all these cubes spawning. That's a Taurus ring here. And here we're gonna do some tricks. What I want to do is I want to have burst count of 10 cubes to be evenly distributed around this ring. of circle. How do we do that? Instead of a random distribution, basically it's gonna randomly put every cube on, the entire ring. I'm gonna do direct. And what happens when you do direct by default is it only designates to a certain point in this ring, right? So if you go, say, U position of like 0.5, it goes to another point on this ring. So instead, what I would do, and something I discovered, something called execution index. And if you choose a normalized execution index for the U position, then your cubes that's being spawned, 10 of them, are being placed evenly around this ring. So that's pretty cool effect. And after that, I want all the cubes to face to the center. So right now they're kind of all placed in their original orientation. And basically I want them to all orient towards the center. And how do we do that? We can create another node here, orient mesh to vector. It gives you a look at direction, right? This look at direction gives us direction to all the cubes all at the same time. However, I want each individual cube to look at the center. In order to do that, we need to here do some sort of a Niagara node magic here by creating a new scratch dynamic input. And let's call this one orient to center. What a scratch dynamic input is kind of a custom blueprints you can create inside of Niagara. So it makes Niagara super powerful when you can do custom things. So in here we're going to create an input that gets the position value of each cube when they're being spawned, right? Because they're basically each have a unique position. So you just type in position here, and then we're going to find this particle position. Secondly, we need to create a vector 3 input value. So it's called a new vector 3, and then you can double click this and change the name of this variable. Let's call this look at position, right? Very cool. So this value we're gonna change or input later. To solve this and convert this into a vector, sort of a normalized vector value, what we need a node called a normalized distance range, a node that will calculate the vector based on these two input values, right? So the original position and then a look at position. So we're gonna hook the position as the start position of the particles, and then the look at position to be the end position, right? And then the distance, don't need to worry about that. And at the end, all we need, let's make this a little bit bigger, the normalized vector between positions. So we're going to take that and send it out as an output, and that's all there is. If we pop back out, this orient mesh to center has this orient to center 01 that we have created. The look at position, we can go and take this box and type in engine owner position, simulation position. All right. So now they're kind of all pointing towards the center, and that's kind of the effect I was looking for. Next, what I want to do is add a force, a constant force, so that all these cubes can radiate outwards. So to do that, I'm going to go add velocity from point, right? Whenever when you see these red warning boxes, it's not a big deal. 9 out of 10 times you just click on this fix issue and then it fixes for you. So in this case, if you click on that, it basically adds this apply initial forces to this chain of modules. So by default it's set to 100, but if you can see in the preview that it's still not moving, that's because in the particle update we need something to solve this velocity. Type in solve. So we got solve forces and velocity. If you don't have it, then it will not actually make it move. Now we have this moving, can press compile and save. And let's take a look in the preview here. Voila, so we have sort of like star of cubes radiating out from the center. Pretty cool. Let's continue. Now we're gonna finally get into creating another custom module taking the spectrum audio analysis data and affecting all of these cubes. And before I get into that, I want to quickly talk about what is actually audio spectrum. Basically, as you all know, audio volume meter that you have seen probably in recording software, so basically it tells you how loud the volume is, right? What spectrum data does is laid out from left to right and low frequency on the left and high frequency on the right, right? So basically one end represents low frequency and the other end represents high frequency. And of course our ear can only hear a certain range of frequencies. And you can think of the whole spectrum at any given time as representing the entire range of sound that's being outputted. And this data can be represented in bands or so-called resolutions. That's why you have these bands here. In reality, the real frequency has infinite resolution. But in digital sound or especially in visualizing spectrum, we can pick and choose how many bands we want to visualize. This is basically what a spectrum analysis data can look like in a very basic form. It's very two-dimensional. Keep that in mind. So we hop back into our Niagara system. Basically what I do with audio spectrum is I use it to affect the scale or the size of my mesh, right? So in the particle update, I'm going to go ahead and add mesh scale size here. For the mesh scale size, it's asking for a vector 3 value, so XYZ in scale. And what I do is I will turn that into a single float value. So I type in float here, and then you go from vector from float. What that does is use just one value, do a uniform scale of your mesh instead of doing a vector 3. Because this mesh scale size value is referencing the initial mesh scale, so we're going to go back to initialize particle here and tick from by default is unset, and we're going to change that to uniform scale, and by default it has a scale value of 1, and that's fine. From here what we would do is we're going to add our custom new scratch dynamic input here, and let's call that audio spectrum float, meaning that it's going to output a single value at the end of this. And what's great about these dynamic inputs is you can reuse them for in other places, in other modules and instances. For the purpose of this tutorial, we're going to use this to only affect the size of our particles. We're going to add an input node and then just type in spectrum, new audio spectrum. You can drag out from that, type in spectrum, pick audio spectrum here. This is what's wonderful about Niagara system is it has audio spectrum analysis module built in so that you don't have to take that from outside of the blueprint, for example. You can do your analysis all within Niagara. You have this thing called normalized position in spectrum. This took me a while to figure out what that actually meant. Remember this picture that I showed earlier? It goes from low frequency to high frequency in a linear fashion, kind of from left to right, right? So what that normalized value is asking is basically the position of the spectrum from 0 to 1. 0 meaning, for example, low frequency, and 1 is the high frequency. If you just put in, for example, 0, then it's only going to output all the spectrum data from the lower end of the frequency. So it's just like one value, right? So ideally what you want to do is you want to put in a value based on each particle, that each particle position, or in this case what I'm going to demonstrate is using the particle age. On the input node here, we're gonna add something called normalized age. And normalized typically means it's a value from 0 to 1. And we're gonna connect that to the normalized position in spectrum. So basically, depending on the age of the particle, meaning that when it was born is 0, dies is 1. And our particle system, if you look at the initialized particle here, is set to lifetime of 5 seconds. I hope that makes sense. And this last input channel index is basically 0. 0 is like left channel audio, 1 is right channel audio, so it's stereo sound. You only have 1, 0, and 1. In most cases, I only visualize mono, which is just left channel audio, so you can just leave that as 0. And once you get the value out as an amplitude, so you want to maybe scale that somehow to actually see what's happening, because if you scale it just from 0 and 1, it could be not very much of a difference. Also, you want to add perhaps a default value so that they don't start out as 0, which is you don't see it. What I would add at the end of this is basically a multiply add node. Basically helps to reshape the value to something that's more useful. So I'm gonna create 2 more input nodes here. So I'm gonna add 2 floating variables here and change the name for the first one. Let's say call that magnitude, and then the second float is gonna be our default size, right? You can kind of guess what we're going to do with that. So we're going to multiply by the magnitude and then add our default size and then output that as our final value. Once you apply, you can actually go back and change the default value of these. Here you have to again put it back to 1 because I created the scratch module first, so it doesn't take default value. For the audio spectrum, create a user parameter. So you can also select, say, master submix default here, but instead of doing this here, I would create a user parameter because I found out that if I don't do that, then I have to open up this Niagara system in order for the audio analysis to work. If you go to this user parameter section here and then click on add and then type in spectrum, and this will be available in your Niagara properties. And here I can just assign master submix default, and master submix default is kind of one of the default submixes that comes with the engine. I didn't create this, and what that does is it will take all the audio that's coming from your level or your scene. For the resolution, I leave it at default, which is 512. Again, it's 512 band of resolution in your spectrum analysis. Minimum high frequency, I leave it as default as well. So I'm going to compile and save this and go back to my scale mesh size. Here I'm going to open up this list, and the first thing you see is this new user parameter that we have created. So we're going to use that. I think we're ready for our initial test. In my project, I have some music loops that I've created loaded here. You can kind of hear what this sounds like. And it's already previewing in my preview window. But what I'm gonna do is I have created something called a sound cue, and you do that by right-clicking on your audio, and then just pick Create Cue here. And this is the sound cue that I've created. If you double-click on it, what I did is I added a looping node here, so that way my music loop will loop indefinitely when I place it into the level. So you can just drag this looping node here and then connect your output to here and then output to output. I can delete this old one, and this is how you make your music loop forever. And I'm gonna place this sound cue into my level and organize it under the audio folder. A quick overview of what I have in the scene here. These are all default sort of a scene that I've deleted all the unnecessary things. So the only two things that I've added is my music spectrum analysis Niagara that we'll be making, and then this sound cue. Hit play here, you can see that this music is playing in my level and it's affecting Niagara. Now let's make it a little bit more dynamic and interesting. So let's go back to our Niagara system. Look at our values for default size and magnitude. I can shrink my default size a bit, say 0.3. Yeah, make my magnitude bigger. Let's make the audio effect a bigger size, maybe a 4 to try it out. And I'm gonna go back and make my Taurus Ring smaller, 75. Cool, let's take a look. Yeah, it's already creating a very sort of interesting shape. A lot of working with Niagara is you don't always know what you're gonna get, so you kind of have to experiment and manipulate with the values to almost discover interesting kind of results. And this is kind of already looking kind of funky. Let's keep going. Yeah, I'm gonna put my windows side by side here. So normally I wouldn't recommend working like this, but what I found is this preview window in Niagara is not a true representation of your particle system because it needs to continuously run, and this timeline will just stop at however many seconds. So what I would do is I will play my level and constantly change my values in my Niagara system to see it update as it's playing. So that way I can continuously work on it and without stopping and kind of like going back and forth too much. First thing I would try to change is maybe I make this lifetime longer, so it has longer legs on these array of cubes. Next, maybe I add a rotation to the cubes. Let's go ahead and add rotational velocity. Again, click on this fix issue button. Oh, and you also need a solver in the update. So let's solve the rotational forces to have it actually apply the rotation. And I think my rotation value is too high. Let's try 1 first. Oh my god, that's cool. X-axis. Oh, that's already looking pretty psychedelic here. Let's keep going. Let's push it a little bit, because right now we're not having technically that many particles. We can go much more. The spawn count, I can crank it up to say 30. Now we have this audio reactive kind of a sun ray thing going on. What you can do is add a little bit of noise in here to make it a bit more organic, meaning that in the particle spawn, and not in the update, but in the spawn, I'll add a curl noise force. Let's fix this issue here. Cool. So for the curl noise force, I changed the noise strength to 30. I cranked down the noise frequency to 0.1, so this is a bit more detailed. And I take the pan noise value and give it a little bit of pan, so the noise field will kind of evolve in time. So it's not static, right? So the noise is not sitting still. And let's take a look at our results. Cool. I think we kind of made like a sound flower type of thing going on that reacts to the music. Not bad. Leaning towards the psychedelic side of visuals, but it's pretty cool. You can see there's some details here with all these cubes spinning. That's pretty crazy. And you can see that this is very responsive. It's running pretty fast because there's not so much geometry here. FPS. Yeah, so it's running at 60 frames per second on my Full HD resolution output here. So there you have it. This is one of the first tutorials on Niagara spectrum analysis in Unreal Engine, and many of you have requested, so it took a lot of time for me to plan and shoot and edit this video, so please do like and subscribe. If you do have any tutorial suggestions or questions or comments, you can leave it in the comment section below. And finally, you can download this project on my Patreon page.